Hello engineers, welcome to the new video of the course, and in this particular video we will try to plot the transfer characteristic for this particular transistor, that is IRFZ44N and IRF540. Okay, so before plotting the transfer characteristic curve, as I had mentioned that we need to focus on threshold voltage, and over here where it is, over here you can clearly see that the threshold voltage, we always take the typical value, and I had told to you that how exactly we calculate this particular typical value. We take average of minimum and maximum value, right? This is what we do, and this is the typical value which is obtained, right? But before coming to this particular conclusion, we also need to focus on the transfer characteristic curve, and you can clearly see this is the transfer characteristic curve, okay, for this particular MOSFET, that is IRF Z44N. Okay, so you just have a look over here. When the temperature is around 175 degrees Celsius, so your VGS would be, the threshold voltage would be around 2.8 2.9 volts. But if your temperature is around 25 degrees Celsius, so the threshold voltage is around 4 volts, 4.3 volts, something like that. Okay, alright, so now that we had assume certain values at 25 degrees Celsius, so remember one thing, at 25 degrees Celsius the threshold voltage for this particular transistor, that is IRFZ44N, it is how much? It would be around 4 volts to 4.2 volts, something like that. Okay, great. So now what I will do, I'll just go on the Multisim software. I'll just cancel this, since we had already finished since we had already plotted the transfer characteristic for this particular transistor, that is 70007. So what I'll do, I'll just delete this. And I'll just click on this particular transistor. I'll again go to the MOS enhancement N channel, and over here I'll write IRF Z. Let me check the model number. I'm not so good in remembering these values. Yeah, Z44N. Okay, Z44N. Okay, so I'll just select this, click on OK. Great. I'll just connect this particular MOSFET with the sources that are available over here. And as I said, over here VGS can be anything, but since we had assigned the values for VGS from 0 to 5 volts, as you can see, just a second, let me just save it first. Okay, so go on simulate, click on analysis and simulation, and you can clearly see my VGS should increase from 0 to 5. It should increment with the step size of 0.1 volts. Okay, and the output is IVDS, that means the current flowing between the drain and source. Great. So now what I will do, since I had already assigned those values and all, so I'll just run this particular simulation, and I will obtain the graph for this particular eMOSFET or N channel eMOSFET. Alright, so you can clearly see over here graph for this particular N channel eMOSFET, and you can clearly see over here, see the current is almost 0, right? The current is almost 0, and now as I am approaching this particular value, that is, what is this value? 3.74. It should be around 3.8, right? So my graph is increasing, right? The graph is increasing exponentially, or rather my current is increasing exponentially, right? This is what I can say, right? Okay, I hope you are able to understand this particular point. That means what? My threshold voltage is around 3.8 volts. It is around 3.8 volts. Okay, I am again repeating it. My threshold voltage for this particular transistor, that is IRF IRFZ44N, right? Yeah, IRFZ44N. It is around 3.8 volts, as you can clearly see, 3.7432, right? Okay, so the another way to verify this particular threshold voltage for this particular transistor is just by double clicking on this particular component, that is IRFZ44N, then click on edit component in dB. Then you just need to move a little bit down, and then you just need to find out the threshold voltage, that is VTO, right? Let me go a bit down. Just a second. Yeah, over here you can clearly see the threshold voltage, which is 3.56214, as you can clearly see over here. If you want, you can take screenshot of it and then try to zoom that particular image, so you will get the appropriate value. Or else if you are doing it with me, if you are simulating this particular circuit with me, you can easily check this particular value. It is 3.56214. okay, so this is what we concluded over here. That is from this particular graph, 3.74 or 3.5, which is very much close to this particular value. 3.5, 3.6. yeah. So the threshold voltage for this particular MOSFET, it is around 3.5. And if you look over here, we had just guessed a random value just with the help of this particular graph, which would be around 4 volts, right? Which would be around 4 volts, but the exact value is around 3.5 volts, right? The threshold voltage for IRFZ44N is 3.5 volts, and if you look over here, the typical value is around 3 volts, right? The typical value is around 3 volts. Okay, so I hope you understood how exactly we calculated, or how exactly we reduced the threshold voltage. Okay, because the threshold voltage is not going to be stationary as it used to be in case of BJTs, right? The threshold voltage for BJTs or VBE for BJTs, it used to be set at around 0.7 volts if it is made up of silicon, and if it is made up of germanium, it used to be at around 0.3 volts, right? But in this scenario, it is not going to be constant, since my threshold voltage, it is dependent on temperature, so it will vary according to the temperature, right? Great. Now okay, by the way, this particular graph, see this particular one, just a second, let me just a second, DC sweep and DC sweep. Okay, so you can clearly look over here, this particular DC sweep is of 2N7000. okay, because for that particular transistor the threshold voltage was 2 volts, and the threshold voltage for this particular transistor, that is IRFZ44N, it is around 3.5 volts, right? Okay, great. I just revised the concept. Okay, I didn't taught anything over here. I just revised the concept. That means what? Again, to show you that the threshold voltage is changing with respect to temperature, and also it is different for different transistor, and that's why I had intentionally taken 3 different transistors to explain you this particular concept. And now we will focus on the third one, that is IRF540. As you can see, IRF540, and as I already mentioned that the threshold voltage for this is, again, it is around 3 volts, but we will look upon the graph that is given over here where it is. Again, if you look over here, for this particular transistor as well, the threshold voltage at 25 degrees Celsius, it is around 3.8 3.9 volts. Okay, something like that. Okay, so let me go to the Multisim software and let me select the transistor as IRF540. Okay, so let me delete this particular MOSFET and let me select the transistor as IRF540. IRF540. Okay, let me just click on it and let me just place it somewhere over here. Let me erase it. Sorry, let me cancel that. Okay, and which way? So I just need to connect it to the voltages. Connect the gate, drain and source terminal of this particular MOSFET to the respective voltages, right? And I'll just cancel it, and let me just save this particular diagram first. Then I will again go to the simulate, analysis and simulation. I will not set anything because already I had set this particular parameters, right? I will just check once again. Okay, because nothing should be changed over here. It should remain as it is, as we had set during the plotting of the transfer characteristic for 2N7000, right? Great. So let's save that. Let's run it. Alright, so this particular curve or this particular transfer characteristic is of IRF540, and you can clearly see over here. And now let me take the cursor. You just click over here, show cursor, and you just focus on this particular point, because after this particular point the graph is increasing exponentially, as you can see. and this particular point is 3.58. okay, so as I mentioned, just a second, yeah, it's around 3.58. okay, so this particular point is your threshold voltage for IRF540. so the threshold voltage for this particular MOSFET is, or this particular transistor is 3.5865. let's verify it once again. So how do we verify it? So for that we need to double click on this particular transistor, then click on edit component in dB. Then yeah, since we are dealing with IRF540, so you just double click on it and let's move down and let's check where they had provided the VTO or the threshold voltage. And yeah, you can clearly see over here the threshold voltage is 3.55788, right, something like that. You can clearly see over here, and I had highlighted it, and this is what we are getting over here in the transfer characteristic as well. So I'm cancelling this particular window and I will just zoom this particular window, and you can clearly see the in the transfer characteristic curve for IRF540, the threshold voltage that we are getting, it is 3.5865, right? So that means the threshold voltage for this is, I mean, for this particular transistor is for this particular transistor is how much? 3.5865, and you can clearly see in the data sheet as well, it is roughly around 3.8. as I mentioned, since we cannot guess, I mean, we cannot guess the appropriate value, but we can just have a random guess based on this particular transfer characteristic curve that they had provided. And also if you look over here, this time they had not provided the VDS. okay, so it also depends on the VDS voltage. So that's why if you look over here, to you it may seem that, you know, the VTH for this particular curve, it would be around 3.8 volts, but in reality it is around 3.58 volts, right? Great. So I really hope that you understood, or you at least got a basic idea that how exactly we can, you know, take the value, or how exactly we can find out the value for threshold voltage for different transistor, right? What is the typical value, how we exactly get the typical value based on the minimum and the maximum values of threshold voltage. I at least hope that you understood the basic idea, okay, of what exactly the threshold voltage is, right? Great. So what I'll do is that I will end this particular video over here, and in the next video we will simulate another circuit. We'll try to, you know, glow certain LEDs based on this particular concept or based on this particular idea. Okay, so thank you for listening me patiently. I'm ending this video over here. Thank you.